Ever wonder what you're really made of? Like way down deep, past the cells and the molecules and all that.
I know what you mean. It's like, what's the very heart of it all?
Exactly. Well, get ready, because today we're diving into the world of quarks.
Ah, quarks. Those tiny particles that make up, well, pretty much everything.
They're like the ultimate building blocks of matter. And here's the crazy part. They're not just some abstract physics concept.
Right. They're actually key to understanding this whole quantum technology boom that's happening.
Exactly. That's what Yorgo Schneeppert really gets into in his article.
Yeah, Schneepet's work is fascinating. He really breaks it down.
So before we go any further, let's start with the basics. What are quarks? I mean, I know they're small, but
Imagine, if you can, zooming into an atom, which is already incredibly tiny, right?
oh yeah, mind-blowingly small.
Well, quarks are even smaller. They're what make up the protons and neutrons inside the atom's nucleus.
Whoa. Okay, so if atoms are like, say, houses, then quarks would be like
The bricks, the cement, maybe the foundation.
the bricks. I like that. So are all quarks the same? Or,
Good question. Actually, there are 6 different types, what physicists call flavors. Up, down, strange, charm, bottom, and top. It's kind of a quirky naming system, I know.
yeah, scientists and their naming conventions, right? But out of all those flavors, Schneeppert seems most interested in the up and down quarks. Why is that?
Because those are the ones found in every single atom that makes up you, me, and everything we see around us.
No way. So I'm literally made of up and down quarks.
You got it. Every atom in your body contains these little guys.
That's wild. I mean, that's both amazing and a little freaky to think about.
Definitely mind-bending. And there's another layer to this whole thing, too, because Schneeppert mentions that quarks can't exist alone.
Right, right. There was something about confinement.
Exactly. It's as if they have this intense need to be together, always found in groups.
So they're like the ultimate party animals. They can't stand to be alone.
Something like that. And what holds them together in these groups is this incredible force, the strong force, one of the 4 fundamental forces of the universe.
Okay, stop right there. Strong force. Is that like some kind of cosmic superglue?
You could say that. And the glue, so to speak, is actually made up of other particles called gluons.
Gluons. Okay, this is getting really interesting.
Right. And the whole theory behind this mind-boggling interaction is called quantum chromodynamics, or QCD for short. I know, a mouthful.
QCD sounds like something out of Star Trek.
Right. Even Schneeppert admits it can be a tough concept to wrap your head around. Basically, it says that quarks have this property called color.
Hold on, color. Like actual colors, like red, blue, green.
Not quite. It's not actual color, but more of a way to describe how they interact through this strong force.
So it's like these tiny particles have their own secret language of color, and that's how they communicate.
It's a good analogy. Think of it like each quark carries a color charge,
Hmm.
and that determines how they interact with each other.
Okay, that's wild. So we've got these quarks. They have their own color language, and they're held together by this powerful, strong force. But how does all of this relate to quantum technology?
Ah, that's the exciting part. Think of it this way. Quantum technology is all about manipulating the very building blocks of reality, right?
I get that. But what's more fundamental than the particles that make up those building blocks?
Exactly. We're talking about the most basic level of matter here.
So you're saying quarks are like the ultimate quantum Legos.
Precisely. And by understanding how these Legos fit together, how they interact, we can potentially build more powerful, more stable quantum computers.
Now we're talking. I mean, everyone is buzzing about quantum computers these days. But I had no idea quarks were involved.
Oh, they're essential. Schneeppert makes that very clear in his article.
So how does it work? Are we going to be building computers out of quarks?
Not exactly, though that would be pretty cool. It's more about using our knowledge of quark behavior to design better quantum bits or qubits.
Qubits, those are like the heart of a quantum computer, right?
You got it. So it's like we're learning from the masters, these tiny particles, to build the next generation of technology.
Okay, that makes sense. But why should I, a non-physicist, care about all of this? What's in it for me?
Well, imagine faster drug discovery, personalized medicine, materials lighter and stronger than anything we have today. That's the kind of future that understanding quarks could unlock.
Okay, now you've got my attention. This is starting to feel a lot more relevant to my everyday life. So we've got these quarks, they're bound together by the strong force, and they're somehow going to revolutionize technology. But wait, didn't Schneeppert also mention something about groups of quarks called hadrons?
He did. And we've actually already talked about one type of hadron protons and
Oh,
neutrons.
right. They're made of 3 quarks each, if I remember correctly.
Exactly. But there's another type called a meson, which is made of a quark and an antiquark.
Antiquark. Hold on. Are we talking about antimatter now?
We are. Antimatter is this mind-blowing concept where essentially for every particle of matter, there's a mirror image antiparticle.
So there's like a mirror universe of antiquarks out there.
In a way, yes. And mesons, because they contain both a quark and an antiquark, are crucial to studying antimatter.
Okay, my brain is officially exploding. So we've got quarks, the strong force, quantum computers, and antimatter all connected.
It's all part of the same incredible story. And as we continue to explore the world of quarks, we keep uncovering new chapters, new possibilities.
I think that's a perfect place to take a break and let our listeners catch their breath, but don't go anywhere.
We'll be back after a short break to delve even deeper into the world of quarks and their impact on the future.
Okay, we're back, and I'm still trying to wrap my head around all this. Quarks, antimatter, quantum computers, it's a lot.
It really is, but it's also incredibly exciting, you know?
Yeah, I mean, who knew that these tiny particles could be so important?
Right. I mean, Schneppet really emphasizes that in his article. It's not just theoretical physics, it's the foundation for some incredible technological advancements.
You mentioned earlier that studying quarks could lead to breakthroughs in medicine and material science. Can you give me some concrete examples? Like, how does that actually work?
Sure, let's start with quantum computers. One of the biggest challenges right now is building quantum computers that are, well, stable and reliable.
Right, because quantum information is so fragile.
Exactly. It's easily disrupted. But by understanding how quarks interact through the strong force, scientists think we can actually design more robust qubits.
Those quantum bits that are the foundation of quantum computers.
You got it. So it's like learning from the masters of stability.
The quarks.
Precisely. And think about the implications. Quantum computers could revolutionize drug discovery.
Really? How so?
We could simulate complex molecules and design new drugs with incredible precision.
So we could tailor treatments to an individual's specific genetic makeup.
Exactly. Maximizing effectiveness, minimizing side effects.
Wow, so personalized medicine could actually become a reality.
Absolutely. And that's just one area. What about material science?
Yeah, how can quarks help us build better materials?
Well, remember how we talked about the strong force being the strongest force in the universe?
It's what holds those quarks together.
Right. And Schnepphat suggests that by harnessing that same force, we could potentially create ultra-strong, ultra-lightweight materials.
Okay, but how?
Imagine building airplanes or spacecraft out of materials that are lighter than a feather but stronger than steel.
Now that's just mind-blowing. But is that even possible? I mean, it sounds like science fiction.
I know, it's definitely early days, and there are huge technical challenges. But the potential is there, and scientists are actively exploring these possibilities.
So it's not just pie in the sky thinking. There's actual research happening.
Oh, absolutely. Schneppet even talks about research at CERN.
CERN, the European Organization for Nuclear Research.
That's the one. They're using particle accelerators to study quark behavior.
Right, CERN. They have that giant atom smasher, the Large Hadron Collider.
Exactly. And by smashing particles together at incredible speeds, they can recreate conditions similar to those just after the Big Bang.
Whoa. So it's like looking back in time to the very birth of the universe.
Pretty much. And by studying these collisions, we can learn more about quarks and how to maybe one day harness their power.
Okay, that is officially the coolest thing I've heard all week. But you know, I have to admit, I'm still a little fuzzy on some of the technical details. Earlier, you mentioned quantum chromodynamics, QCD, that theory that explains how quarks interact.
Mhm.
Can you maybe break that down a bit more?
I can try. Remember we talked about quarks having this property called color?
Yeah, like their secret language?
Right. Well, QCD basically describes how these color charges interact through the exchange of gluons.
Those gluon particles that act like glue.
Exactly. It's like each quark has its own little color palette and they're constantly exchanging colors with each other. And the rules of QCD, they kind of dictate how those colors combine and change.
So it's like a super complex game of color swap with these tiny particles.
Okay.
I think I'm starting to get it. But why is this so important?
Because QCD is crucial for understanding the behavior of quarks. and ultimately for unlocking their potential in quantum technology.
So if we can crack the code of QCD, we can maybe design new materials, develop more stable quantum computers.
Exactly, and even potentially understand the mysteries of antimatter.
So it's like QCD is the instruction manual for the quantum world, and we're just starting to figure out how to read it.
That's a great way to put it. And as we learn more, we're opening up this whole new realm of possibilities.
Okay, this is all incredible, but I have to ask, Schneppet didn't really mention any drawbacks or potential risks associated with all this. Is there a downside to understanding quarks so deeply?
That's a really important point, and honestly, one that Schneppet doesn't really address directly. I think it's crucial to consider the ethical implications of any scientific advancement, especially one with such far-reaching potential as this.
Right, so as we delve deeper into this quantum world, we need to make sure we're using this knowledge responsibly.
Absolutely. It's not just about what we can do, but what we should do.
Well said.
Yeah.
This has been a truly fascinating deep dive into the world of quarks. We've covered so much. The strong force, quantum computers, antimatter.
It's amazing how it all connects, isn't it?
It really is. But before we wrap things up, I want to touch on one more area where quark research could have a major impact, and that's quantum communication.
Ah, yes, quantum communication. That's another exciting frontier. You see, one of the biggest challenges in quantum communication is ensuring the security of the information being transmitted.
Right? Because quantum information is so delicate, so vulnerable.
Exactly. And that's where quarks could come into play. Schnepphat hints at the possibility of using quark properties, like their color charges, to develop new methods for secure quantum communication.
So we could use quarks to create unbreakable codes.
It's a possibility. By exploiting the unique properties of quarks and the strong force, we might be able to develop quantum communication protocols that are virtually impossible to hack.
That would be revolutionary.
Yeah.
It would change the entire landscape of cybersecurity.
Absolutely. And it's just one more example of the vast potential that quark research holds.
It's mind-blowing, really, to think about. We started with these tiny particles, and now we're talking about revolutionizing everything from computing to materials to communication.
It really is remarkable the ripple effect of these fundamental discoveries.
And to think, we've only just scratched the surface.
Exactly. Who knows what incredible discoveries await us as we continue to explore this quantum world.
It's exciting to think about. So we've covered some pretty mind-blowing stuff. I mean, quarks, gluons, the strong force. It's amazing to think that these tiny particles are actually driving some huge technological leaps.
Yeah, it really is. Yorgo Schneppe, in his article, lays it out really well. They're not just some theoretical physics thing anymore.
Right. We've talked about quantum computers, we've talked about new materials, but earlier you mentioned quantum communication.
I did.
What's so special about quantum communication?
Well, imagine a world where communication is totally secure. I mean, like, physically impossible for anyone to eavesdrop?
Okay, that sounds amazing.
Wow.
But how do quarks fit into that?
Remember how we talked about quarks having those unique color charges?
Yeah, like their secret language.
Exactly. Well, Schnepphat suggests that we might be able to exploit those very properties to create unbreakable codes.
So like each message has a special quantum key, and only the sender and receiver know it.
That's the idea. And because these keys would be based on, well, the fundamental laws of physics, they'd be virtually impossible to hack.
Wow, that would be huge. Think about it. Online banking, military communications, everything would be so much more secure.
Absolutely. It would completely change the cybersecurity landscape. And it's just one more example of how this deep dive into the world of quarks could change so much.
It's mind-blowing, really. We started talking about these tiny little particles, and now we're talking about revolutionizing communication, computing, material science, like everything.
It really highlights how interconnected everything is, you know? From these tiny particles to the vastness of the universe, it's all governed by these fundamental laws.
It's humbling, for sure. So as we wrap up our deep dive into the world of quarks, what's the one thing you really want our listeners to remember?
I'd say the biggest takeaway is that quarks aren't just this abstract concept stuck in some physics textbook.
Right?
They're the building blocks of our reality, and they hold the key to some pretty incredible possibilities.
Absolutely. Well said.
Yeah.
And for our listeners who are now like obsessed with quarks, where can they learn more?
I definitely recommend checking out Jorgo Schneppet's article, Quarks, Fundamental Teilchen der Quantentechnologie.
Right. It's a great read. It's fascinating. It really gets you thinking about all the possibilities.
It does. And who knows, maybe someday we'll look back at this as like the dawn of the quark age.
I love that. The dawn of the quark age. All right, well, that's all the time we have for today. Thanks for joining us on this deep dive into the amazing world of quarks. Until next time, keep exploring and keep asking questions.